Okay. So I'd like to thank you all for coming to this installment of the Quantum Fluids and Isolation seminars. So today we have Professor Jan Zaanen from Leiden University speaking. So Professor Zaanen got his, he graduated in chemistry from University of Göttingen in 1982 in Göttingen, the Netherlands. And in 1986, he got his PhD in physics from University of Göttingen. He postdoced at the Max Planck Institute in Stuttgart, Germany in 1987. And in 1999, he was a visitor at AT&T Bell Labs in New Jersey. In 1993, he was awarded a 5-year fellowship at the Lorentz Institute for Theoretical Physics at Leiden University. And in 1998, he joined Leiden as an associate professor, and from 2000 to present, he has been a full professor at Leiden. He's been a visiting professor at Stanford University, the École Normale Supérieure, and a fellow at the Newton Center at Cambridge University. He is a recipient of many awards, including being a fellow at the Royal Dutch Academy of Sciences, being a Solvay professor at the Solvay Institute in Brussels, Belgium in 2012, fellow of the American Physical Society. In 2006, he won a Spinoza Award, and he is also the first author of the book Holographic Duality in Condensed Matter Physics, which really inspired me to become interested in the field as well. So please help me in welcoming either by muting yourselves or virtually, Professor Jan Zaanen.
Okay, thank you, Joshua. I continue to find these webinars kind of a weird experience, right? I'm sitting here at home, and especially at 8 p.m. usually it's my relaxation time. So I hope I manage to get some energy in the talk. I'm not entirely sure. Yeah, and I won't actually wonder what the heck is now going on. Why this? Whoops. Hiccup.
You might have to click the slide first.
Click slide first.
Yeah.
Weird. Yeah. Okay, thank you. Yeah, so I mean, I kind of wonder about it. I think I share this kind of strongly with Subir that, you know, we are getting old men, and whether we like it or not, physics has been rather slow. Yeah, right. So the thing you have to ask in your life is, as a physicist, when I'm done with it, is will any of it stick? Will it be so that anything I saw happening, or better, I was involved in, will actually be remembered 100, 200, 500 years from now? And I'm kind of excited because in the last years, I feel myself in sort of a flow. It's surely a community effort type of thing, but I'm sitting right in the middle of it, just kind of accidentally. It's sort of a good feeling that things are really happening. That, you know, when you look in a number of years from now, that this will be something really central to all of physics. Now, one source of inspiration is surely that coming of the quantum computer. Surely it's a great machine, but it's more that the thought is that we have to think in terms of information, right? And this sort of constant information thinking, even on a very basic level, I find myself as rather enlightening, and that's really what this talk is about deep inside, right? So, what is the big deal with these quantum computers? It's entanglement, right? So we were forced to think harder about it, this exquisite quantum mechanical phenomenon of entanglement that you best understand in an information language. What is it? Everybody knows the EPR story, right? That you have two quantum bit spins whatsoever, and these occur in these different configurations depending on Hilbert space, and you take a coherent combination of two of them. And then suddenly you have this sort of spooky axial distance, blah, blah, and you have used to build a quantum computer. Now, the trouble is that when you have 3 bits, you already live in an 8-dimensional Hilbert space because you have 2 to the power 3 different possibilities. But the physical world starts out on a microscopic scale basically as a quantum computer itself. Right? So it's made out of quantum bits. There are about 10 to the power 23 of them. So we live in this extremely big Hilbert space, as large as 2 to the power 10 to the power 23. And now it, of course, happens, actually all the time, that in the time evolution, coherent superpositions are formed out of all these 2 to the power 10 to the power 23 states, right? And so everything is kind of literally entangled with everything, right? It's this quantum many-body thing. And the fact that the quantum computer can actually handle these extremely large Hilbert spaces / information flows that oops, weird, that John Pascal to the idea that you could call it quantum supremacy, which I find a great marketing word. So in principle, we live in a completely incomprehensible world where we're completely overloaded with information. So how can we make sense out of it? So let's ask the question, what is matter? And you can look into your high energy textbook or your condensed matter textbook and you get an answer. And we started to appreciate that it has been kind of a cherry picking because these are always a special, extremely special states. So they're called short-range entangled product states in the lingo of quantum information. How does it work? It's very simple. So look at the table. That's a piece of matter that exists at zero temperature. How do you make it quantum mechanically? You make an array of real space wave packets and you plug in one atom per wave packet and there's your solid. And so that is the product state, which is a classical state of no entanglement. And then you're supposed to dress this up with perturbation theory, and what it does to you is basically work in some local short-range entanglement, and therefore these states are short-range entangled product states. So basically anything we have learned in school is of that kind. Also, the PCS superconductor is obvious, and also the Fermi gas, or better the Fermi liquid when you dress it with perturbation theory. So the question arises, should all concepts of matter be of that kind? There should no theorem, right? Actually, it's a bit the other way around because the whole way of understanding stable states of matter you can basically reduce to a mathematical exercise. And the mathematical exercise basically turns into a statistical physics partition problem, right? So you recrotate Lorentzian time to Euclidean time, imaginary time, right? And then your quantum path integral, gets the form of a statistical physics partition sum, and then you use this stochastic method of statistical physics, right? And you compute the stable states of matter. However, that you can do this is in a way exceptional, because a generic quantum problem will be characterized by a non-stochastic structure, meaning there are negative probabilities, and the problem gets very ill-defined. So a typical example is fermions that are strongly interacting at a finite density. They suffer from this so-called fermion sign problem. And actually, there is this claim theorem by Troyer and Wiese, claiming that such a signful fermion problem is generically an NPR problem is equal to a quantum supreme problem. Right? So states of fermion matter that are short-range entangled products are should be in a way exceptional. Yes, they happen a lot, but there's no reason that it should happen all the time. Right, and I would like to crack it, and you can talk with Matthias about it, who is now one of these ideologists of the quantum computer business. And Matthias will tell you that he was fighting his whole life with the fermion sign problem, didn't get anywhere with a classical computer, and then decided that a quantum computer should be built, and he endeavored on the pursuit of making that thing, right? Problem is we have still to wait quite a while before that thing is there. So we can actually ask the question, where else to look for this kind of physics, which is a priori, of course, uncomputable, right? We don't know anything about it mathematically, and it may be around us, and we just don't see it because we don't have the tools to recognize it. And that brings us to high TC superconductivity, right? That's in the meantime an integrated problem that started in '86, which is discovered by these two gentlemen of superconductors with TCs that were way higher that would thought back then to be possible. So TCs climbed in no time to 140K. It was happening in these complicated pieces of rusted copper. Now, some of us are a bit older, have lived through that enormous hype that broke loose, blah, blah. And in the course of time, I'm here extremely opinionated. It worked itself more and more into a complete mystery problem. Some people call it intellectual crisis, but I don't think that that exists, because intellectual crisis means there's something to discover, right? And you may have to be patient. It's not easy to make money with it. Right, so when it started, basically everybody was thinking in a paradigm that was established in the 1950s based on short-wave and thermopodic state, that is the thermal liquid turning into a BCS superconductor. And then in the course of time, every time some new experiment came online, it was first unleashed on the cuprates. And you know, the progress in condensed matter experimentation over the last 50 years has been breathtaking. All kinds of new machines came online, like scanning tunnel spectroscopy, the resolution of existing machines improved dramatically, photoemission in fact 10 to the 5, etc., etc. And the bottom line is, whether we like it or not, the people in the community, the more we learned about that stuff from experiment, the more mysterious it became. When you don't want to admit it, you don't understand the heck of it, you miss the point. Right? And that's precisely the attraction of this problem. There's something going on out there that is sort of regular, it's physics, that we don't understand at all, and we know the root of the problem. And it wouldn't be a side problem, we would have solved this in 1987. Okay, when you want to know more about it, I have really not the time to go into any depth. A little while ago, we wrote a consensus document for on request of Nature, and you can look it up. I think it's still kind of timely, and there, you know, this big picture, basically with this agnostic school of thought woven into it, you can enjoy. So a very gross overview, what is it about? People always show you the so-called phase diagram, how does it work? You start out with an insulator. It's insulated because of extremely strong electron repulsion. Mod insulator, it's basically a quantum mechanical traffic jam. That you start to dope in the same way as you dope semiconductors, and you get sort of motion of the traffic stop and go motion, and you get all kind of interesting mysterious phenomena like the pseudo gap and intertwined orbits, etc. You continue doping, the conductivity gets better and better until you have an optimal doping, and then it goes down again. And the king of this landscape, to my strong opinion, is this strange metal phase. And I think I share that with many people. And the attraction of this strange metal is that on the one hand, it behaves in an extremely simple ways that have proven in the course of time to be really incomprehensible. The simplicity is the big mystery. So a way to address this is, sorry, I skipped a slide. Right, so the kind of iconic experimental quantity that's always mentioned in this context is the simplest of all physical quantities, the electrical resistivity. Right, so when you have a normal system, particle system, blah, blah, and you look at the resistivity, then it's basically like the thermally excited quantum particles are like little cannonballs. And these scattering against each other, and the scattering mechanism is a some function of temperature. It has to be. So at low temperatures, you have electron scattering, and so on, and you get electron-phonon scattering, you can get all kind of temperature dependence out of it, and then the inelastic mean-free path gets of order of the lattice constant, and the resistivity saturates at the Joffre-Regel limit. Right. So the morale is, in a system that we understand, the resistivity should be an interesting function of temperature. Not so in the cuprates. In the cuprates is this perfectly straight line, sort of beginning at the melting point of the crystal at 2000 Kelvin, or something of the kind, and going all the way down until the resistivity disappears because you are at TC. Right, and this linear resistivity is so interesting. And the way to highlight that is just to do an old quote by Bob Laughlin. I don't know. With my apple, a linear resistivity reflects an extremely simple behavior, and extremely simple behavior in physics need a powerful principle for the protection. Explain this principle. My apple is doing this. I don't touch anything. This thing is changing back and forth. Hopefully it stops. So my answer is this universal principle is rooted in quantum supremacy. I forgot to say, so the belief is that these trace metals are about extremely densely entangled matter, where the entanglement is due to the design problem. It shows these very weird properties because these reflect generic properties of very densely entangled matter. And the simplicity of the linear resistivity may find a natural explanation in terms of such a principle. And I will explain it at the end of the talk. That's really the aim of this presentation, to tell you that story and getting it into a good perspective. Now, to get there, by the way, don't hesitate to interrupt me. I love to get questions, and I will slow down when I get a question. So to get there, the real news is that we got help of the string series in the form of this ADS-CFT correspondence or holographic duality. There are a number of names for it. That should be interpreted as a machinery that allows us to compute a particular form of very densely entangled quantum supreme matter, be it in a particular limit, but it seems to reveal a very general principle. And this general principle we may see in the experiments in cuprates. I'm a strong believer of it because it really works for me quite well. When you think of holographic things, then you just get a kind of clear view on all the things that don't make sense, which means something. So I will do a very short summary of it. I really don't have time to get in any depth. And then I will basically go into non-equilibrium physics. There will first be a part of highlighting the whole idea of quantum thermalization, eigenstate thermalization. Then I will go to a sort of real-life holographic result that is about spectroscopy and thermalization. And then I will get back at explaining to you the linear resistivity. So that's the program of the remainder of the talk. Oops. Good. Okay, let me try to do ADS-CFT in less than 10 minutes because I need half an hour for the main dish. So I refuse to really explain it. You can basically think about it as, brilliant mathematicians have figured out your machine is like a Fourier transformation, and you learn it by doing exercise, and when you finally have a grip on it, you find it's sort of a normal thing. This is the way I think so. Here, for the first time, it's extremely absurd. So the claim is as follows. There is an infinitely large universe that is governed by Einstein's famous theory of general relativity. And that infinitely large universe has an outside boundary. And these things we have figured out a mathematical mapping that's like a Fourier transformation with lots of turbos and other catches on it. That makes it the most powerful of all Fourier transformation-like phenomena in nature. They map this gravitational physics on a purely quantum physical world in flat space, blah, blah, in the boundary that is in 2020 best understood as a quantum physics that is in this densely entangled limit of life. So this is rooted in the gravitational holographic principle, saying that when you're dealing with gravitational theory, there are far fewer degrees, there are far more degrees of freedom. So it's as if you have to live in a world with one extra dimension in order to capture the degrees of freedom of the normal non-gravitational flat world. This is called a holographic duality because it's really a beautiful metaphor. So how does a normal hologram work? So you have this photographic plate with complicated interference fringes. You beam through a laser beam, and it reconstructs for you in three-dimensional space a picture that is very recognizable, like a little green tiger. This is precisely the way that this ADS-CFT duality works, right? Because you relate the world in one lower dimension, it's incomprehensible with abstract interference fringes. With the world in one higher dimension, that is gravitational world, is actually quite a bit more comprehensible. Einstein's theory is something that we can sort of understand intuitively as humans to a degree. You go to interesting movies with black holes, and they tell you a lot about how that works. Right, so the bottom line is, There's this machine, now it's a mathematical machine, you unleash the formidable powers of Einstein's theory in the bulk. So everybody who knows the R a bit should be very impressed by the enormous mathematical missile behind it. That makes possible to get all kind of very universal things to work in the bulk. You pull it to the dictionary, right? This duality, and you get to see all kind of behaviors of this extremely strongly entangled quantum matter. And you rely now on the uniqueness of the GR solution to really do sort of a classification, a very systematic mapping of the kind of things that can happen in that densely entangled world. This started with the kind of plain vanilla Maldacena ADS-CFT conjecture. Yeah, it was back then a conjecture. I think in the meantime it's just ADS-CFT. And it took us in condensed matter a little while to realize that in this plain vanilla ADS-CFT, you're actually addressing physical problems that are very familiar to us. We can be grateful to Subir. He played a crucial role in Leiden connection. So the thing that is familiar to condensed matter physicists is the quantum critical state. How does it work? You have some ordered state, then you have a zero temperature control parameter that is increasing the quantumness associated with that order, so it starts to fluctuate more and more and more. You get a phase transition at some critical coupling. This is basically the same thing in the classic, meaning sign-free bosonic type of systems that we understand, as a classical thermal critical state of statistical physics, and that expresses itself in the form of this famous quantum critical wedge. Right, so when you're getting inside that wedge, you see the world of quantum critical phenomena. You get outside the world, it's the world of the normal ordered states. The physics in this quantum critical wedge is the same physics as computed by ADS-CFT, plain vanilla. So how does it work? Once again, you write down basically an action that's like 5/4, which is also a set Fish model when you think about time as an extra dimension. And then it's very important whether you are above or below the upper critical dimension. When you're above the upper critical dimension, the self-interaction 5/4 is irrelevant at the fixed point, and you just get free field theory. So you convert this into quantum physics by doing Wick rotation, you compute propagators, and they just describe free particles, right? Okay, there is perturbation theory going on, but in the scaling limit, it just becomes free scale invariant modes. You dive under the upper critical dimension, and there the self-interaction is relevant, and then actually hell breaks loose. It's sort of a public secret, but any statistical physics expert you'll ask about it will tell you that the critical states, that the strongly interacting critical states, actually empty hard. You cannot quite compute it on a classical computer. The good news is that you can get extremely good estimates for the things that matter, because the only thing that can matter are scaling exponents. The critical state is scale invariant, therefore all physical responses, blah, blah, are algebraic. And when you're algebraic, the only thing you have is the values of the scaling exponents and anomalous dimensions. And these get strange values. And these are the anomalous dimensions. And you get responses, physical responses that are these branch cuts. So how do they look like? Here's an example. This is critical, strongly interacting fermions. Dirac fermions, Lorentz invariant fermions, right? So you have the light cone. Let's first sit at K is 0, momentum is 0, right? And what you have when you look at the propagator is just this spectral function that consists of this long algebraic tail. You go to a finite momentum, you boost it up. So when you're outside the light cone, there's no signal. You hit the light cone and bang, the thing goes up. And again, it shows a long tail. right? So this was actually computed in the first paper that appeared in Science using ADS-CFT. And it was computed with ADS-CFT, and precisely this kind of physical response is hardwired in the correspondence. So for that, you have to think about the meaning of that extra dimension, right? So this is a representation on gray disk that is friendly to your eyes of an entity space. That is a space characterized by a negative cosmological constant, hyperbolic space, a very generic solution of vacuum Einstein theory. And you see that this has this strange habit that's infinitely large, but still has a boundary, right? And the field theory lives on this boundary. So there's space out of the field theory, you have this extra dimension. Now, when you look at UI, with your eyes added, at this drawing by Escher, right, your eyes discern that there's a notion of fractality of scaling variance in it, right? And that is the conformal invariance that's baked into the isometry of the geometry. And I use all the professional words. The beauty is that when you now want to understand what the meaning is of this extra radial direction in the field theory, it is the scaling direction, right? So when you're very close to the boundary, you look at the very short distance physics of the theory, that's your view of the theory, you dig deeper and deeper and deeper into the bulk of ADS, you go to the deep interior, and there you describe the longest time, the longest wavelengths. This describes the scaling direction in the quantum field theory. In the boundary, in the sense that you, as usual, integrate out short distance degrees of freedom and make it this flow in space of Hamiltonians, where you go to lower and lower energy. And the fractality of the geometry translates into the conformal invariance, scaling invariance of the field theory, and therefore you get all these algebraic response, all these branches, blah, blah. Good. Oh yeah, on the side, a branch grid means that there are no particles in the theory, right? The particle is a pole. In the theory, you don't have it. And it is very simple. In order to have particles, you need this semi-classicalness, the fact that your thermodynamic state is actually not entangled. And that gives you the possibility to localize the quantum numbers the localized quantum numbers which stay together are called particles. When you are dealing with this densely entangled matter, your ground state is already very densely entangled. Everything is entangled with everything. Your excited states have to be orthogonal to it. So they're also all delocalized in a very big Hilbert space. And it's impossible when everything is entangled with everything to identify a particle. Right? So generically, we call quantum supreme matter being characterized by unparticle physics. No particles out there. And sometimes hard for us to work with because we are trained to think particles. Okay, this perhaps to surprise Subir when he's still awake. There's one menace in the whole business, and the menace is that you have only a gravitational dual of your quantum field theory when you're living in a matrix field theory in the large n limits. Typical example is Yang-Mills theory, right, where n is the number of colors and you have n squared gluons. Right? That n squared is really a device to handle that situation. We don't have these infinite number of gluons, blah, blah, in condensed matter systems, right? So it's a headache. There is, however, something that I learned from a friend, Guido Vidal, who is in essence claiming that when you go to that large n limit, you go in a very specific way to a limit of maximal entanglement in CFTs. Right, so his basic claim is, so yeah, in a bit more detail, it's about constructing these Mira scaling invariant tensor networks. And they can say, in order to keep the same accuracy, I have to have a certain bond dimension, and the bond dimension is really a measure of how densely many-body entangled your system is. And there's evidence, and we try to get more evidence for it, that the bond dimension has to grow like e to the power c, where c is the central charge, and central charge goes to n squared. So when you go to this large c limit, claim is that you have sort of a maximally entangled quantum critical state. Now the news is you take that stuff, and now you can play games, right? So the critical state by itself has not so much physical properties. You need to know this kind of a couple of other things you're interested to know, but then you're done. So around 2008 or so, the string theory started to experimentalize with condensed questions. Okay, what is the question? Finite densities, only interactions, fermions, blah, blah. That last thing, they were not quite aware of it. These things can be all encoded in this bulk computational language. That was really very shocking for myself to learn that the first thing that rolled out was a metallic state that was largely called the holographic strange metallic state because it looked so much like the strange metals we had met in the ITC laboratory. Doing all kinds of other stuff, it can form condensates that are familiar to us, like superconductors. You can even cook up thermal liquids and all kinds of orders you see in the cuprates. It's all very natural. I just want to basically download one ghost message. I mean, the big deal is really strange metals. And in order to make some sense of how these work, my favorite way to think about them is being strongly interacting generalization of the thermal liquid in the same way that a strongly interacting critical state, what she's talking about, is a brother of the non-interacting critical state that you have above the upper critical dimension. Right? So it was you have these engineering exponents when you are in a non-interacting critical state. These get strange values, anomalous dimensions. So when you're dealing with a thermal liquid, the specialty is that on the one hand, you have what I like to call the zero sound sector, very collective excitations, and then you have the continuum particle Hall excitations, right? The Lindhardt continuum. Now, when you look at the thermal liquid, everything out there is algebraic, but it's not algebraic in the sense of a literal conformal field theory. It's not a conformal field theory. The structure of scaling is different, but just think, you know what you learn in school, like the Lindhardt continuum behaves like omega squared at low energy, right? And that's an algebraic form. So what you learn from holography is that you have basically the same deal. You have again a collective sector where sound lives, where you have hydro, and then living side to side with it, there's this continuum of things that is a bit like a Lindhardt continuum, except that it's now characterized by all kinds of interesting anomalous dimensions that are, according to our computational friends in holography, organized in a very, very interesting way. It's like canonical scaling. I give a couple of underlying scaling dimensions, and from that you can reconfigure it in scaling dimension of physical observables. This kind of stuff seems to get through in experiments. A good example is the measurement of the dynamical charge stability. It's really striking how much more it is like a holographic state metal than it is like thermal liquid. But I have no time to go into it. Already 5 minutes late, right? And Joshua already advertised the book. It's still, I think, timely to get kind of an overview of the state of the art 5 years ago. Not that much happened since then. Good, guys. This was basic introduction, and I would like to start a talk. It's less better than you perhaps think, because the introduction is a lot. Are there any questions? If not, I continue. Because I will change gear right now. Change gear to a perhaps somewhat different sounding subject. It's again all rooted in this many-body entanglement. And it's this whole business of quantum non-equilibrium and especially quantum thermalization. I guess that in the meantime, everybody is kind of familiar with Eigenstate thermalization hypothesis. I learned it not that long ago, and I was shocked when I learned it. It was again one of these, revelations on a very basic level coming out of this quantum information thinking. Right, so the precise protocol of the Eigenstate thermalization, invented by these gentlemen in the early 90s, is prepare at time t is 0 a state that is a coherent superposition of energy eigenstates narrowly distributed around the mean. And this is about the many-body system, and these highly excited energy eigenstates we are interested in are always very densely entangled. Ground states can be quite product-like, but when you go up in the spectrum, at some point everything is densely entangled. Then you let your system go, as you learned in school, with unitary time evolution, and now it comes. You now want to know a physical quantity. And unfortunately, we live at the wrong side of the collapse. In other words, all we can see is webs of local operators, probabilities. Right, so A is the operator associated with observable. You take the expectation value, you get these horrible oscillatory terms. And the claim of eigenstate thermalization is, when you wait long enough after a thermalization time, that the answer you get for the expectation value of this observable cannot be distinguished from what you would get in an equilibrium thermal ensemble, characterized by this thermal density matrix. We'll meet this in a moment in a little fashion. That's what kind of shocked me or woke me up whatsoever. That the way it really works is our relationship to this unitary time evolution, this extremely big Hilbert space, the quantum supremacy business, blah, blah, is any local observer gets overwhelmed by the enormous amount of quantum information in the physical world to such an extent that he or she does not better than it actually becomes a thermal state at a long time. Right, so you have this enormous information flow going on in a unitary time evolution, but you can only mine a logarithmically small part of that information. It's like the output of a quantum computer. That's a bad thing. And therefore, you get just extremely confused. I like to think that many physicists find it very intuitive, because when we try to explain something that we find simple to a non-physicist, usually in no time that person thinks that we are either nerds or drunk or incoherent whatsoever, right? That's a fact. And I find it very helpful to think about it that way, and perhaps I should have realized this in my first year of physics study, but nobody will explain it to me that clear. Now I want to play a game. So, of course, that whole world around us is like this. That gas that we are breathing behaves like a set phys, very stochastic affair because of the reason you just saw. You can only see the vessel associated with that gas, therefore the full unitary time evolution of the extremely densely entangled exact energy eigenfunctions that happen at these rather high temperatures of a gas, blah, blah. But we know what happens because at the end of the day, Boltzmann told us how a gas works. It's the cannonballs are flying around, they collide against each other, do a lot of everything, blah, blah, and it tells you precisely how the gas works. So the question arises, are there circumstances where this metaphor, which is classical system of variables / molecules whatsoever, is actually failing when we do the quantum thermalization of visual exercise? Okay, I want to do an example. It's very, very elementary, and I find it really a shame it's completely ignored. It's not quite due to me. I was more sort of assistant in this business, was really figured out by a former graduate student of mine with the name Laughlin, who is now in Geneva, and is addressing this awfully famous affair called atom physics, right, where you have the cloud of atoms in a reservoir, and then and you make it very cold, and at a certain time you suddenly take out the trap potential, and it flies away. And by looking at the way it flies away, basically claiming this is just a system of expanding ballistic particles, right? You can work your way through to the initial condition by making a little picture of how the clouds are expanding, and it tells you how things like the initial momentum distribution look like, right? And from that you can see that you get Bose-Einstein condensation and so forth. So we'd like to do that. So Let's take a example of a one-dimensional system, mostly to show this picture. You can do it also in higher dimension, no problem. And we make a reservoir with walls where we trap particles that are a bit hotter and a bit denser than the vacuum surrounding it. And then at time at t0, we take away the trap and the particles fly away. We assume it to be ballistic. And what do you get when you compute this classically? You get, say, for the density in the middle of the trap, as a function of time, this brown line. That's very obvious. Okay. So now we would like to compute this quantum mechanically, and actually it's quite hard to load up real wave function, real particles, and you do the Fermi surface. There are quite a number of them, and the trouble is that these same oscillatory factors that you just saw even kill the computer when it comes to computing this for free particles, where you start out with these sort of more involved initial configurations. Luke figured out that it's way smarter to use the modular Hamiltonian in the unitary time evolution instead of the Hamiltonian itself. And the modular Hamiltonian is the log of the density matrix. You know it or you don't know it, you can work it out. The bottom line is because you can find a temperature, and it seems that modular Hamiltonian is sort of more economic in retrieving information that you pick up with your vest whatsoever. This works extremely efficiently. You can basically compute anything you wish. Wait a moment. Yes. So we can do precisely the same exercise I just showed, but now fully unitarily. And the outcome is this blue line. There's a blue line. When you look carefully, you see that here the blue line is seen behind the brown line because everywhere else they're identical, right? And these are extremely short times. So the bottom line is, yes, you get it right. When you do the full unitary time, evolution, complicated wave functions, blah, 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 blah. You take vest of it, and it precisely reproduces this general wisdom that you get the Boltzmannian world back. But now you can actually play games. Now, one thing you can do is consider this classical system, make it collision full with interactions, and then the expansion of your cloud would look like this, right? It's diffusive, you see, it's like quadratic. So what Luke discovered just by accident is take a reservoir filled with radical bosons, embed that in a bath, a vacuum made of these identical bosons, but at low density and at very low temperatures, close to the Bose-Einstein transition. Then let your free particles, non-interacting particles, expand. And what they actually do is they do a collision-full expansion. They behave as these interacting classical particles for the reason that there are these subtle quantum correlations building up when you approach the Bose-Einstein transition. Right, so the morale is that actually, under certain conditions, it may well be that is Boltzmannian metaphor, right, that your quantum particles just turn into classical particles when they are a bit hot, blah, blah. That may actually fail. And this is a simple example I know that makes that case. And this is the interesting big deal. Keep it simple. Look for these circumstances where you get dynamical phenomena that cannot be possibly understood in terms of a classical finite temperature physics metaphor. Good. Now I want to explain to you a situation that I perceive as maximally provocative in this context. It's a very natural thing. It's done all the time in laboratories called pump probe spectroscopy. So how does it work? You have your little piece of material, you hit it with a very intense short laser pulse, right? And that excites everything. You can do it in a unitary fashion, unitary pulse, and you prepare precisely this initial state of the ETH. And then you let your system evolve in time and you probe it with linear response means. right? And that's called pump probe spectroscopy, and you do that as function of time. Right, so this is a widespread thing. When I was a grad student, it was already a business using picosecond lasers, and now people are trying to do it as attosecond laser. That has been the big difference during my career time. Now the thing is that you can do a surprisingly literal modeling of this in this holographic black hole language. I will save you all the details. All you need to know is that we do a pump probe experiment in a holographic trace metal. We can actually do a series pulses. So this simplest pump pulse you can imagine is this Gaussian blob. You look in the power spectrum, and it's all concentrated by at zero frequency, but you can give it this oscillation, right? Pulse shaping is called, and then this distribution moves to a final frequency, and it's basically the kind of thing you do in ETH. So that is this distribution of Eigenstate around the density distributed around the mean, blah blah. And then we can actually measure the optical conductivity. We just take the protocols as you find it in the meta literature, so you can compute the full frequency dependent conductivity as function of time after the pulse. And what would you expect? What you would expect is something of this kind. So first explain what it is. This is the real part of the optical conductivity, right? So it's the frequency dependent conductivity of the system. When you have a system in a Laughlin continuum, then it will be characterized by a delta function at 0. It is a perfect metal, that's the meaning of it, because the Laughlin invariance, everything turns perfect metal in the Laughlin invariant system. And then here we gave it a small momentum relaxation time, and therefore it turns into a Drude peak. This is a Lorentz delta function, where the width is the momentum relaxation time rate. Then you go through a minimum, and this stuff here you can interpret as sort of holographic independence. It's something else, but don't worry about it. And this is the brownish line is where we start. So we start at a small but final temperature. What do you expect? You hit your system with a pulse, it will heat. And when you make your system hotter and hotter, the optical conductivity is supposed to do what you see here as function of time, right? And when you wait long enough, it will eventually reach this final thermal equilibrium state. You do this as holography, and you don't get out this natural result. What you get is the following. It's extremely boring at first sight. You start out with the same initial thermal state. You switch off your laser directly after the pulse as soon as you can. Then you measure the optical conductivity as soon as you can. And the optical conductivity reflects the state of the system in its final thermalized equilibrium state. According to holography, it does not take any time to thermalize. Like ETH is saying, after some time, we don't know how long, we will be in a thermal state. This thing is telling us that when you do it in a state metal, blah, blah, which is extremely dense and entangled, it takes no time to land in a thermal state. Reason, you're maximally entangled, and therefore you lose any understanding of what's going on there really in really no time. There's a beautiful gravitational interpretation. This goes back to Minwalla. I mean, the trace metal is really not important. The reason is really very universal, and it's all wired in the causality structure of GR. So for those who know how penthouse diagrams work, this is the penthouse diagram of the business. This is this famous radial direction in the ADS bulk. This is the boundary time. At this moment, the pulse hits, right? This is a literal laser pulse. And that means that in the bulk, you release a null shell. And null means it moves in with velocity of light. This was a toy problem figured out by Mr. Vaidia in the 1930s as a toy problem for the collapse of a star in a black hole. So it is the shell of dust that is falling in. And now you have an interesting special causality effect in GR. You look at the space-time directly after the shell is released. And this space-time thinks that already the black hole has formed. So it takes no time to think that there's a black hole out there. Because a causal observer, somebody who's doing a two-point measurement in the boundary, can only measure this wedge in the Penrose diagram. That thinks that you have a geometry that's a black hole geometry. Black hole means in holography finite temperature, right? So there's this remarkable business that the finite temperature state is dual to a Schwarzschild black hole in the bulk, and the horizon area is equal to the entropy in the boundary, and the temperature is Hawking temperature, and it's all these black hole quantum black hole systems that are all working literally in holography. Is very remarkable as well. Right, so this is the reason that you think that you have instantaneous thermalization. So this is not because Zubier is still in the audience, I think, when he was sleeping. Actually, this was also computed directly in the large C zero density CFT by Johnny Sonnet, all really to the force. And there was an equal or even more to the force by Zubier and co-workers computing it in SYK. And in both cases, you find for two-point propagators the same instantaneous thermalization, right? So it is somehow related to this dense physics, dense entanglement business. Oops, I really have to hurry a bit. I just skipped this except for announcing that actually it hasn't been quite observed, this ultra-fast thermalization, for the reason that the machines are not yet good enough. Right, so electronic thermalization happens very rapidly in the present state of the art of fast experimentation. You can't quite resolve the electronic thermalization in metals. It goes too fast also for simple things, but the bottom line is so the generation of machines coming online right now may be good enough to actually resolve it. Right, so this actually right now worked on. I spent a year sabbatical in Stanford. Good friends is Shen and his group, and one of his group members is actually having a separate ultra-fast time resolved photoemission affair that would be very good for these purposes. Good. 5 minutes left. Are there any questions? Okay, I think I can do this last part in 5 minutes. Let's try. Yeah. So we really learned a lot from these Sony interacting quantum critical system Zubier style. And when you read this famous book about quantum phase transition, you'll figure out that a lot of the book is dedicated to this case. That when you switch on, when you take your Sony interacting critical state, that's scaling invariant at a critical point, and then you switch on temperature, you can make very universal statements. It's very simple. Right, so how does it work? You have to think Euclidean particles, and perhaps you learned in school that you are in temperature there by making the time axis in a circle with a radius h bar divided by kbt. So when t is very low, imaginary time is very long, and when it's t is rather high, it's very short. And the deep sort of discovery is, you have now to ask the question, I do measurements on a time scale long compared to the length of the time axis, what do I get? Answer is you have to compute it, you have to do the equation, it's tedious. And you find out that at these long times, you get a purely relaxational dynamics. Right, so you can write down scaling forms, and now the big deal is that when you have relaxation dynamics, you just have one relaxation time. You can only have a simple relaxation dynamics, and there's only one time scale out there, and that is the length of the time axis. In other words, that relaxation time will be generically a constant times h bar divided by kbt, and the constant is order of 1. I learned this from Zubier a long time ago. At some point, there's a little extra means out there, but it's not very important. I felt it needed a name, and I called it Planckian dissipation. And this name Planckian dissipation, I think it's a bit of a buzzword at the moment, going viral. But I think nice word, you know, it's just sort of doing justice in language of the beauty of these phenomena. So this is all reproduced in ADS-CFT, right? It's generic CFT things, and they are all impeccably reproduced in ADS-CFT, except that now the role of temperature on the gravitational side is fulfilled by a thermal black hole, right? I already announced it, that you have this Beckstein-Hawking entropy and this Hawking temperature, blah, blah. It goes much further, and I perceive that it's the most beautiful thing of the whole agenda. Right, so when you go to a finite temperature and you have a Galilean invariant system, it has to behave like a classical liquid, and there's only one universal theory out there, and it's Navier-Stokes. The beauty is you can now go into the bulk, study these sort of long wave gradient expansion dynamical GR near the horizon of the black hole. That is about long wavelength physics. You pull it through the dictionary, and these equations just turn into Navier-Stokes. It's really astonishing when you see it. So part of the hydro agenda is that there's dissipation, and dissipation is encapsulated in a hydrodynamic liquid by the shear viscosity. This whole business started really in 2002 with the work of these three famous gentlemen. It's very simple. The viscosity in ADS in the bulk, so the viscosity of the boundary fluid is determined in the bulk by the absorption cross-section of zero frequency gravitons by the black hole. That is a universal number set by geometry, by the area of the horizon. So is the entropy density. So when you take the ratio of the two, what you find is, so it's viscosity divided by entropy density, you find a number, 1/4 pi, that's purely geometrical number, times Planck's constant divided by Boltzmann constant. It turns out to be an extremely small ratio of viscosity to entropy density. In normal liquids, it's way higher, and it's called a minimal viscosity. It's actually just Planckian dissipation disguised. So by dimensional analysis, you learn that viscosity should be set by free energy density and a momentum relaxation time. The free energy of a colloid consists purely entropic, so it's S times T. Your momentum relaxation time is just Planckian, right? And you fill it in, and you directly find that these two together imply that the ratio of eta to S should be set by H bar. That's all the same business. Okay, I skipped this, so yeah, big splash when in 2005 it was, 15, it's getting late, but now 2015, no, 2005, it was 2005. It was actually discovered that you can form a quark-gluon plasma, behaves like a hydrodynamic plasma, and this viscosity to entropy ratio is actually very, very close to this minimal value. And then all the high energy physicists were very excited because now we expected it. And this is often claimed to be the first big triumph of holography in physics. Back to the linear resistivity of the cuprates. Oops, I will be 2 minutes late. I can't quite do it in 2 minutes. So the first thing to realize is that actually at least low frequency transport in cuprates is determined by a pretty impeccable true transport. So it's the same business as I showed before when I was talking about the holographic probe experiment. Right, so it's a druid, meaning you have a near hydrodynamical transport. You are not that far from this perfect middle behavior because the system believes it's living in a Galilean continuum, but there is a momentum relaxation rate that is set by the width of the druid peak. You can just measure this in a lab. You find a perfect druid at low frequency, and you find out that all the temperature dependence is coming from the momentum relaxation rate. and that momentum relaxation rate is just Planckian. It's rather literal Planckian. Right? There's a prefect of order 1 here. That's actually the origin of the name, right? So we realized this already a long time ago, and at that point I thought, we give it a good name, let's call it Planckian dissipation. So you can now do again a fairly literal, in a way, holographic modeling. This hard work was really done by Richard Davison. This already a while ago, 2014. Back then it was kind of high tech. So we use sort of the most sexy and cool and credible form of holographic state metals called conformal to Eigenstate. The specialists will appreciate that this is a local quantum critical state. It's really behaved like a marginal thermal liquid in many regards. And it's characterized by a Sommerfeld entropy, like the Fermi gas and the Fermi liquid, right? It's linear in temperature entropy. And then you can break a linear invariance because you want to have a finite resistivity. And that we did back then using so-called a massive gravity. That was back then very fancy. In the meantime, it's the easiest thing you can do. And Richard computed it, computed resistivity, finding out that the resistivity is a perfectly straight line starting out from 0 temperature, there's no conductivity, all the way up to the chemical potential, the Fermi energy. Now, to understand this, it's an absolute
Can I ask a question on that, Jan?
Yeah.
Okay, so
I
understand that you have this holographic model. So what is the equilibrium state? It's a charged black hole with an ADS2 horizon. Is that correct?
I mean, it's conform to ADS2.
Okay, it's conformal to ADS2.
Right? And it's this thing that you have a notional black hole in 11-dimensional.
Yeah, all right. And the M squared. Sorry, go ahead.
White space. It's that thing, right? And doing everything right, there's no constant entropy. That is the fun of it.
So the momentum breaking term is the M squared term.
Yeah.
And do you have to adjust the value of something to get a linear resistivity, or is it generic?
I will get to it. It's not generic, right? Because you need to have some momentum relaxation in order to have final resistivity, and that you get by choosing a mass, capital mass, slash.
No, but my question was, do you get different powers if you choose? Is there some scaling dimension that was adjusted or no?
No, I tell you where it comes from. And perhaps you remember it because, you know, when this spoke a long time ago, I remember that you liked it. It's extremely elementary.
Yeah, I didn't remember that plot. I mean, it's a very nice paper. I remember it. Yeah, sorry.
Yeah, I just explained you the story, and perhaps you slipped your mind, but at that point you even helped us by saying it only works for Z is infinite. Thank you, Subir, for that good advice. Right, so how does it work in essence? The first real big deal is that you have to have this extremely rapid thermalization. Why is that? In order to have hydro, you need local equilibrium, and local equilibrium means, you know, that you have to reach very quickly because there's also a lot of disorder in things like cuprates. Right, so you're basically to outpace the disorder scattering with you rapid equilibration. Right, and that is the real secret. Having said that, you have an hydrodynamical liquid, and Mr. Stokes already explained how the resistivity works. It's shear drag, right? So the momentum relaxation rate is set by the diffusivity of the liquid divided by L squared, where L is the length where the fluid discerns that it's not living in a Galilean continuum, right? So this L is the freely adjustable parameter. So yeah. Then you have the, some people call this the Einstein relation, right? So the diffusivity and the viscosity just hang together. In other words, what you need to know is, let's assume that next to this very rapid local equilibration, you have also the minimal viscosity at work. So eta over S is a constant H bar. Right, so plug it in and you see directly that the resistivity is proportional to the entropy. You have here this non-universal prefactor Subir. When you compute it, you get a reasonable number. There's order of nanometers to get all the numbers right, you know, everything else. That's how it could work. And now we know, right, and measured by a long time ago by these two heroes of experimental physics. It's very hard to measure the high temperature electronic specific heat, but they managed. And we know from that in a strange metal regime, the entropy is Sommerfeld, is linear in T, like this in a Fermi gas. Also true in this conformal radius to funky strange metal coming out of the black holes. So in other words, resistivity goes like the entropy. The entropy is Sommerfeld, goes linear in T. Henceforth, the resistivity just goes like temperature. Okay, just to honor Subir, what you pointed out, Subir, is that normally the disorder potential also run, right? In order to have it not running, to have it marginal, you better take C to infinite. That was a good advice for us. Remember? Good. So this is a basic explanation. Now, I'm really running out of time. The bottom line is we don't know for sure whether this works. It's very simple. You have to figure out is whether this momentum relaxation that you can measure with optical conductivity is actually precisely tracking the entropy, assuming that the disorder is more or less the same thing in the cuprates you have, with a bit of an uncertainty. But there should be something like, oh, you see the entropy changing considerably, you see that the prefactor changing considerably. Can be done, and the data are not quite there. And the real bottleneck is the electron specific heat at high temperatures. Okay, now I'm nearly at the end, but I would like to do this big surprise thing. So just to give a bit of a credibility to what I just was telling, already a long time ago, it was found that in extremely clean cuprates, when you extrapolate that linear resistivity to zero, there's no residual resistivity. It's very weird, right? Because how can it be that the system can completely escape any form of disorder at zero temperature? How can it happen? Much more recently, people looked into much more dirty, intrinsically dirty cuprates, the 204 family, going to optimal doping again finding this disappearance of residual resistivity. If true, this would be very interesting, that you really find, when it wouldn't subconduct, a metallic state of matter that is a perfect metal. And when you do our holography thing, it's very simple. There's no constant entropy, so the viscosity is vanishing at zero temperature. Your fluid turns into a perfect fluid, and the perfect fluid is unstoppable and will not be resisted. So we like this. What it also reveals is that viscosity gets extremely tiny at low temperatures, right? The Sommerfeld entropy is also very tiny. It's a fervency business. And then you can stick in numbers, and then you have to realize that there's this most famous of all dimensionless quantities, which is the Reynolds number. Basically saying when Reynolds number gets very big, your flows will be very turbulent, like this picture here. But the Reynolds number is inversely proportional to the viscosity. So when the viscosity gets very tiny, that Reynolds number gets very large. Now you can now plug in all the numbers. We seem to know all the numbers by order of magnitude. And what we actually do expect that is that when you get onto scales smaller than about a micrometer or something of the kind, that in no time we'll run into extremely violent turbulent flows when you measure hydrodynamical flows on these nanoscales at temperatures close to TC, where this viscosity gets really small. Now you may have picked up that there's this whole interesting development going on with observing hydrodynamical flow phenomena in extremely clean graphene. And you do that by building these special quantum transport devices that can pick that up. And you can now try to do the same thing in the cuprates and try to see whether you can figure out whether there's anything turbulent happening. Actually, André Geim is busy with help of Ivan Boschwitz trying to make these devices. They have some initial results, but not really clear whether these get produced, etc. And it's also in the physics group busy doing this. So this would be the ultimate proof, and you would find this turbulent behavior. I would regard this claim of quantum supreme metallic matter to be proven. Okay, that's my bombshell at the end of the show. I wrote a tutorial paper about it now about 2 years ago, but much of this is still has not changed really, so I would recommend that. and here are another couple of references you may want to look up and you want to know about it. And now for me, time to stop speaking. Thank you for your attention.
Okay. We have a time for a few questions. If anyone wants to either raise their hand or they can unmute themselves.
Hi, I have a question.
It is Dominique, right?
Yes.
Yeah.
So you mentioned that the resistivity should be proportional to the entropy in this hydrodynamic picture, but I mean, I think there's some evidence.
Holographic picture, right? It's all only when you believe in the minimal viscosity of holography.
Yeah, in the hydrodynamic picture with n minimal viscosity. Yeah, but my question was.
It's basically a slide, right? It's really very simple. Stare at it and no secrets.
So my question is that it seems like in some cuprates there is evidence that the entropy is not T-linear all the way down to zero temperature. Maybe there's a log correction to it.
No, it's Louis Taillefer, and I really object against it. Right, so to measure the electronic specific heat at high temperatures, right? The strange metal is there, above TC, sometimes 100 Kelvin, at optimal doping, the lowest you can get is about 30 Kelvin or so in a TC. So it's always at these high temperatures. It's extremely hard to get because the entropy is dominated by the lattice. There were these heroes. John Lorentz did actually the real hard work, and John had golden hands, and he had all kinds of tricks to actually distill the electronic specific heat from the system at these high temperatures. Now, when you look at these data, it is really very nicely Sommerfeld, no logs. Louis and others are only capable of measuring that electronic speed at extremely low temperatures. Now, when you are at extremely low temperatures and you're in the normal conditions, there's a superconductor, there's no trace metal, so all you can do is apply an extremely large magnetic field and suppress as much as you can the superconductivity. You can't quite do it. You're in the middle still of a vortex liquid at these fields that are available at magnet labs, right? And it's kind of, I really don't know exactly what to think. You then see things like quantum oscillations, and you can measure sometimes the specific heat in these large fields. And you look at these at extremely low temperatures, and there you might see something like a logarithmic rise. And then it's claimed that it may actually be correct that it's related to quantum phase transitions. I mean, he has the example. I think, yeah. There's absolutely a quantum phase transition where I may expect an heavy fermion style, Westminster style transition where you may have these divergent specific heats. It's not generic at all for quantum critical states. It's a special effect for rather perturbative noise. Right? So I would like to ask Louis to show me specific heat data in the strange metal regime. I bet that all these log upturns have completely disappeared when you are at the temperatures of relevance to the strange metal. This is an undecided subject, but I would like to see the data directly. And Louis is putting in a lot of interpretation on the way.
Okay, thank you.
Yeah, you get it, right? These are the open experimental questions. I would love to see someone taking up these high temperature specific heat measurements. It's very hard to work.
Oh yeah, but sorry, I mean, you were suggesting that maybe this strange metal state could exist all the way down to zero temperature, right? Or at least I think that's what you were suggesting.
Not quite. So I think we understand something out there, and the something that we understand is that you're dealing with the extremely entangled states of matter, and they are in a way very fragile. I mean, a metaphor is like extremely hard to keep your quantum computer right in these precise many-body quantum superposition things. So the system will try to find out ways to get out of it. Now, one way is do a old-fashioned ordered state, short-range entangled state, like a superconductor. It's not said that there's still, there's entanglement left in the superconducting state. Perhaps there is, but there's no firm evidence for it. In any case, the subconducting order is an extremely classical thing, you know, that is as classical as a table that we have understood a long time, right? So yeah, not quite. It would be beautiful to have a state that's really like holographic state metal all the way to zero temperature. I haven't quite seen it in nature anywhere. There may be sort of a fundamental law out there saying you can never really reach it at zero temperature, but it doesn't matter much because you go up a bit in the spectrum and everything gets way more entangled than you're used to. You've also the SYK model, right? You can make these SYK chains and then have a normal hop, and you find things are very entangled. And in the last moment, when you have a normal hopping on board, it turns into a thermal liquid, right? That kind of thing, but it's doing so at the very, very last moment. This answers, I hope, a question, right? Are these for
Yeah, yeah.
I'd love to see it, you know, the naked singularity, as Peter Little used to call it. It's the same thing with the sort of classic quantum critical points. Nobody's ever really seen the naked quantum critical point.
Yeah, thank you.
Okay, any other questions?
Maybe I can ask a very quick one.
I think this is my graduate student, and he always asks good questions.
So with holography, you always compute at the level of linear response, right? Even in the probe spectroscopy experiments, it's all done in the framework within a linear response. But then at the end,
the thermal liquid, I mean the charm of holography is right that you can do deep non-equilibrium physics. Your GR in the bulk just turns into dynamical GR. It's harder work, but you can still do a lot of things, a lot more than you can do in a controlled way using normal quantum field theory machines.
yes,
Right, so
yes.
it's sort of pending. I mean, we looked a lot at linear response because linear response experiments are great experiments, right? That is the best form of information regarding your system you can get in principle.
Yeah.
Holography is very flexible, but okay, continue.
Yes. But at the end, you mentioned these turbulent flows in the strange metal regime. So those effects, they're definitely nonlinear in some sense, right?
Yeah. So the precise thing is you have real non-equilibrium, say, think pump probe experiments, blah blah.
Mm-hmm.
You have real linear response, and you know what real linear response is, and then you have this nearly linear response regime of hydrodynamics, so that is governed by gradient expansions. Right, so the typical length scales in the flow should be tiny as compared to any microscopic scale. In this case always set by temperature, right?
Yes.
And then you say, okay, what I need is local equilibrium, right? On the scale of these hydrodynamic length scales, everything should be equilibrated, and then I will move it relative to each other on these longer scales, and there things can get again very nonlinear. So that's sort of things. Right, yes. So hydro is kind of more how do you call it, pushy when it comes to these real equilibrium issues, right? So linear response extremely easy because it's really completely equilibrium. Hydro is just the sort of first step away from equilibrium, and it's more tricky. There's more to see in hydro.
Yeah. Okay, I understand. Yeah. Thanks.
Okay, any other questions?
Hello, I have a question. I expect it's likely simple, but you were discussing the thermalization of strange metals in pump probe experiments, and it seemed like the kicker was those thermalize instantly, and that's
exactly.
That's what's so astounding.
Yeah.
But I wonder how can you ever demonstrate? How can you ever show that experimentally, and that's not just in a thermalization time that's smaller than your resolution?
Yeah, I was running out of time. Otherwise, I would have spent some words on it. Once again, we do a variation on a theme, right? That you have these extremely rapid or instantaneous thermalization process was already identified in the pure CFTs. let me see, where are we? Go through the exercise here. Yeah, here. Right, you may be a bit familiar to these heavy ion collision experiments where they claim the quark-gluon plasma. Right, the way it works is that you have these very heavy ions, like lead or something, and you have two of them, and you accelerate them to close to the speed of light. They sort of turn in these pancakes because of the Lorentz contraction, blah, blah, and then they slam into each other. And all that energy in collision is somehow converted into heat, blah, blah, and then you hope that you get hot enough that you get into the deconfining regime of quantum dynamics. Claim? Yes, they managed to get there. Surprise. They have these elasticity thing that's called, so you have to sort of collision that are not head on, right? And then you can see how the fireball is expanding. And from that, you can decide that you are actually dealing with hydrodynamical plasma out there. Yes, there's plenty of evidence now that there's hydrodynamical plasma. There's a bit of a trouble, however, right? Because you start out with something extremely non-equilibrium, and as you equilibrate, think in terms of particle physics, you have quarks flying around and gluons whatsoever. And then in order to equilibrate, a quark has to slam into another quark. That takes a time, a collision time. And then you have to repeat it a couple of hundred times, and then you can think that you are in equilibrium. That's typically the way that equilibrium physics works in perturbative particle physics systems. The trouble is that this stuff is already behaving like a thermalized hydrodynamical plasma in the time it takes for one quark to traverse half the proton radius. You have barely time to meet one other quark. This is called the fast hydrodynamization. And it's generally regarded as extremely mysterious, and therefore you may not have heard about it because the community is not really, putting this in the sales window all the time because they're really confused about it. I kept a couple of my student friends also this course. There were Ishi Ben Krabs from Brussels is also more worrying about the quark-gluon plasma than about other things, They actually think that this is a manifestation of this extremely rapid thermalization associated with the fact that QCD in this regime is just extremely densely entangled.
Okay, I see.
Yeah, and then there are the caveats. So when you go to condensed matter systems, be aware, at some point when you go up in energy, you will meet particle physics. You will meet the Schrödinger equation of chemistry. And you will look at how, electrons hop from copper to oxygen atoms, etc. That is not densely entangled. And it will give a cutoff, right, for this thermalization time. They have to descend to lower energies, and there you may hope that you have that buildup of this extremely dense entanglement, right, where you expect the speed up of the thermalization. There's a caveat, right? So you cannot have infinitely fast thermalization in a system with a UV cutoff like what you have in condensed matter physics will always be a maximum rate out there.
I see. Thank you.
Okay, so maybe let's thank Professor Zaanen once more.
Sorry to be late.
That's fine.
Okay. It was a pleasure. Good to see your faces, but still. Okay, bye-bye.